And the final speaker, here he comes, the final speaker this morning in this session is Professor Jeremy Baumberg, who's going to talk about confining light below the atomic scale to watch molecular bonds.
So, in fact, I decided, since you're getting towards lunch, to give you a bit of a break and inspire a bit more, so I changed my talk title, but I'll show you some of the things on the way there. So what you'll figure out as we go along is that this is a very interdisciplinary area, so I have to thank a huge number of people, both within the nanophotonics group here and a large number of collaborations, which a lot of them are within Cambridge, because it links to so many disparate things. And the previous talk is actually a perfect way to seg into this, because what we're interested in doing here is trapping light to extremely small volumes so we can watch individual molecules, atoms moving around, to really actually see at the nanoscale. And that is actually going to turn out to be really important if we're trying to build nanomachines. So I'm going to look inside very small structures and actually watch, say, the molecules or the atoms we were talking about in the past, see what they're actually doing. So the first bit that we need to understand is this is the optics of metals, because what you learn in undergraduate is that if you have just dielectrics, you can only focus light down to the wavelength scale. And on the scale we want to look at of single molecules, 1,000 by 1,000 by 1,000 nanometers is just enormous. So what I'll show you by the end is that we can use these metals to focus down to even less than 1 nanometer cubed. And the trick is that when I say I take a metal like gold and I shine light on it, you actually shake the electrons in the metal and they oscillate, producing a dipole. Actually, it's not particularly interesting. You can see that the field is concentrated in these two poles here, but not that concentrated. And that actually is how stained glass works. There's a particular color for that resonance, which sets the color of the stained glass. What's more interesting is when I bring a second nanoparticle very close by, as that gap becomes very small, what happens is the electrons here produce a field which act on these electrons here as well as the incident light, and then these electrons here respond in a different way, producing a local field which interacts with those electrons. So it's a bit like dipole-dipole coupling with magnets, which you can sort of feel there's a big distance dependence, except here these are induced dipoles, so it's more complicated. But it has a really ferocious distance dependence. So what happens is the light actually gets trapped in that gap. It gets trapped very tightly, and the color of the resonance shifts. And in fact, in the last few nanometers, it shifts right from the visible spectrum right out into the infrared. And at the same time, you get up to 1,000-fold enhancements of the light in the gap. So the first thing about this area is that you need to build structures, on the scale of, precise to 0.1 nanometers. That's pretty challenging. So that's what we spent a number of years learning how to do. So for instance, this sort of tour de force experiment is not really the way to do it, but what it taught us is that something here must go wrong because this eventually goes off to infinity, and that can't happen. So what actually happens is quantum mechanics comes into play. So when these get very close, you're building up charges either side of this gap, and eventually the electrons can tunnel quantum mechanically through the gap, and that shorts the whole thing in the last 0.4 nanometers. And it turns out, well, we thought that would limit how tightly we can find light. So it would depend on this quantum mechanical distance here, which is a tunneling length, and the radius of this nanoparticle here. What I'll show you at the end is that actually we didn't realize that that radius can be, in fact, a single atom. And so we can confine light very tightly. So the sort of things that we've been able to do with that, it looks something like this. In fact, this is a nice way to make that dimer. I actually put it on a ground plane so that this nanoparticle sees an image of itself in the ground plane, and it looks isomorphic to the dimer. So we, in fact, can build the system much more easily. What we can do here is confine light very, very tightly into the gap and actually look at the properties of a single molecule at room temperature in ambient conditions. So what we're actually looking at here is the Raman scattering of the molecule. So we can see a single molecule, we shine light into it. The Raman scattering means that just a little bit of that photon energy can be absorbed into a bond, and the light that comes off has a slightly redder color. So we collect that light, and actually each bond has a different shift, so we can measure each bond independently. And so if I look at a set of molecules, they have this particular bond here, which is stable. If I actually reduce the molecule in this case, it's a molecule where I can put an electron on it, I change the electronic wave functions on the molecule, so the bonds change slightly. So the vibration shifts here. So what this shows is that I can see the oxidation state of a molecule just by looking at the vibrations. Now, if I look at a single molecule here in real time, what I can see, in fact, is it's digitally shifting around. And so what's going on here is that electrons from the gold, which are induced by the light, these are called hot electrons, can hop onto that molecule there. And when they hop onto the molecule, they actually turn out to stay for a substantial amount of time, seconds is an amazing amount of time. We can see that change on the molecule. And we can actually play with a whole set of different molecules in the gap here. So this molecule here is actually very well connected to the gold. So when an electron hops onto the molecule, it immediately hops off before the nuclei can move around. So we don't see anything as a function of time for this molecule. Increasingly, as I go this way, here I'm changing how the molecule in the center here, which is like an electron sink, how that's connected to the gold, so how the electrons jump on and off, and I can see this very clearly. So we can see single molecules. Now, how does this link to nanomachines? So let me just try and explain what a nanomachine might be. So we're used to this sort of scaling law of electronics. You just make things smaller, and generally everything works more efficiently, at lower cost, easier packing. So that's Moore's law here, very standard, just scaling down. At the same time, chemists have been trying to build more complicated machines from their molecules by scaling up. That's the 2016 Nobel Prize, for instance. But there are limits here, and eventually these meet, and biology is able to construct things on all these length scales simultaneously and put them together to work as nanomachines. But this is the areas of nanomachinery that we'd like to get. So, we'd like to be able to do the sort of dream that people have had for 50 years, that you can make small machinery on this scale. The problem is that this is a complete dream. We can't do anything like that at the moment, because making that is not simply a task of just shrinking things down. We have to build things, and we know it's possible because nature can do it. So here, for instance, an ant carrying 100 times its body weight just hanging upside down, full of beautiful, intricate nanomachinery on many scales. So there are all sorts of different things that you want a nanomachine to do. I just showed you, say, this one here. We can do that sort of thing. We can see a single molecule, but it's all these other things that are really, really difficult. So, there are different approaches. The sort of, the traditional US approach is just try and shrink it. So this is as good as you've got at the moment, little flying things. But it's basically this sort of technology, and it's not going to get anywhere near that. At the same time, the chemists, they build these complicated molecules, but this is an artist's representation. This molecule does not move like a car on a surface. It's basically stuck and gets shifted around. But we know that cells do have intricate machinery, so it's this sort of thing that we want to access. So over the last few years, we've been building up a toolbox of very robust things that we construct. I'll show you just a few examples of them that can actually try and access this. And optics is important here, because if you think about a nanomachine, you can't wire it up to anything. If you want to make it move around, you can't make wires, and you can't use RF, you can't use Wi-Fi, because to make the antennas, you need to have something which is millimeter scale. So light is actually really crucial to make and control and power and actuate and direct nanomachinery, which is why then we've got into this area. So I'll show you a few of the sort of things that look transformative that we've been doing recently. So one of them was we found a way to make gold nanoparticles where we coat it with a special polymer which is thermoresponsive. What this polymer wants to do at room temperature is hydrogen bond to water. But as soon as we heat it a few degrees, what happens is it wants to hydrogen bond to itself, and it excludes the water. So it collapses. So what we can do is take this same thing that I showed you before, and actually, as we heat it slightly, this will collapse down to here, and then it's reversible completely. So it beats the very strong van der Waals interaction in the system. Now, what I showed you is that as I change the distance there, the color of the light in the gap changes, and I can see that very directly. So what we can do is we can track this in real time, and then, of course, when we can shine light on this, we can actually heat the polymer around 10 nanometers of it just by using the light. So we can make this very fast and optically actuated. And what's most interesting is that we find we can generate forces on the nanonewton scale. And that's about 100 times larger weight for weight than anything we've had access to before. So, typically we have piconewton forces available to us on the nanoscale. So this is one of the things that's enabling us to make sort of locomotion. I showed you already that we can look at electrons traveling on and off molecules, but we can actually start to gate that. So we can control the electron movement around our nanomachine and use it sort of as power and as memory. Then another technology we've been working with Ulrich Kaiser's group for the last few years on is this technology of DNA origami. So it's a wonderful constructional tool. You take a long length of viral DNA and you put in staple strands which staple this bit of the DNA to that bit of the DNA, and it folds up. And if you add 30 strands, you can fold up rigid three-dimensional structures. So you can make, say, an object that looks like that with different materials a few nanometers apart. Or something like this, where we make this nanoparticle mirror structure again, and we put specific molecules in specific locations. So what we can, for instance, do is look at taking that technology and adding it to that technology to start making deformable machines which will actually flap their way on. They'll move just by light. And what you want to do with that is to be able to control it with the color of light, so we can move them all in particular directions. And that's the sort of area we're trying to go into. At the same time, we can actually use this to look at different molecules. So we can use molecules to make spacers where the optical field is very strong, and use it to actually look at very small numbers of molecules, for instance, in your urine. So we're running a project at the moment called the Intelligent Toilet, where we're actually able to detect neurotransmitters at very low concentrations in your urine to be able to actually watch people's brain states over very long periods of time. Perfect. So I'm going to skip that one there. So essentially what I want to summarize is to give you an idea that we can construct these sort of objects where the relevant size scales here, so this might be a 100 nanometer nanoparticle, and it might be spaced 0.9 nanometers from the substrate. We can do that extremely precisely, and we can put particular molecules in particular positions and start to, for instance, look at redox chemistry or more complicated chemistries and control these. We've also found, I haven't shown you yet, that actually we can see if you have a single, I'm looking at the middle bit of this, if I even pull a single gold atom out here, it turns out that we can actually localize the optical field just around a single gold atom. And it's a bit like the lightning rod effect that we're all taught. It's actually a lightning rod effect on the single atom scale. And it turns out it works. Nobody thought that was possible, but now both calculations and our experiments show that indeed when we do that, we actually localize the light there, and we can see it because we look at single molecules when we do that. So we can see Raman spectroscopy. And in fact, what we can do is we can start to make individual bonds here vibrate very, very strongly. So we get to this field of optomechanics. It links to structures. In fact, it links to the gravitational wave detectors, which are 13 orders of magnitude bigger, because basically you have a vibrating spring and an optical cavity. And this is exactly the same thing. This is a tiny cavity with a tiny spring in it. So now, from this we know, if we go back to this formula, that actually the size of this radius can be actually that single atom there. So we get to something which is about 0.1 nanometers cubed for the optical mode. So what I hope I give a sense of is that this opens up all sorts of interesting directions. We can look at electrochemistry at surfaces in real time, which has been a mystery. And in fact, catalysis itself is quite a mystery, as John was talking about before, because people haven't had tools to look in ambient conditions about what's actually going on when molecules attach to a surface. There are also ideas that you can use these as very low energy switches, so for computing and optoelectronics, and also as quantum emitters. So actually it plays towards this area of making particular sort of photon states on demand. And then there's a lot of interaction to chemistry. And in the end, I think the really interesting direction is to be putting all of these things together and using light to actually control and move around and construct nanomachinery. So that's the sort of direction that we're trying to go in. So I hope that gives you a vision. Thank you.
Thanks very much, Jeremy. There's an awful lot to take in there, but we do have plenty of time. Yeah, Charles.
So I'm intrigued that you can see this focusing from a single atom. Is that an issue? Because that means you need atom control of your surfaces in order to know what's happening.
Yes, that's a very good question. If only we could make that structure and have it stay there. What it turns out is when you put a nanoparticle on a substrate, say a metal like gold, the atoms on the outside actually can move around at room temperature.
It's more like a liquid.
Yeah, so it's a bit like a liquid surface. So what happens is it seems to go to single crystal when you put it this way, because the van der Waals attraction here is hundreds of atmospheres. So normally it looks absolutely flat, which is a bit interesting, weird. Then when I shine light on it, it turns out I can actually optically put forces on the atoms. We don't know how yet, but what happens is that you actually have to shine light on it to pull a gold atom down. We see it happening. If we turn down the light power and it's low enough temperatures, it'll stick there, and we can see it. And then if we add back light, we can get it to go back. So that's great. I mean, it's fantastic. We can use light to move individual atoms around and see them. However, we would love to actually keep them there, and that's one of our real problems at the moment for this sort of idea is at room temperature, these move around quite a lot. We can see them on millisecond timescales, and we would dearly love to stop them. So if anybody has any great ideas, I'd love to hear about it.
Don't use gold.
Other questions? Can I ask a really naive one, Jeremy? When I was young, we talked about currents, and they've simply become plasmons. And is there a simple answer as to how a plasmon differs from a current?
No, I mean, you can actually do a lot of this. We have a model here which looks exactly like circuit theory, right? So essentially, this is you can think of the nanoparticle as an inductance and a capacitance, which gives you a resonant frequency. And you can couple it to another one through this capacitive coupling there, and you can use that model to basically predict where the light is. So, but the reason lumped it's not obvious you could do that, because at these size scales here, I mean, they're much smaller than the wavelength of light. It's not obvious that you can use this sort of lumped elements to be able to describe the system, but it's a reasonable approximation.
Okay.
Yeah? So
I might come back to you some more later, but won't take people's time. Any other questions for Jeremy? Okay, in which case we're very close on time for lunch, and I just want to thank all 5 speakers this morning. It's been a fantastic tour of the lab, I think, and really great stuff for those of us who tend to just focus on one thing most of the time. So thank you, everybody, for that.